This is week 3 progress report for Robot Hockey Group 4. Assignments this week, we had to continue on with building our microcontrollers, as well as we looked at the global environmental and economic impacts and considerations from this project and robotics in general. And the majority of this was written in our report already, but we do have it mentioned here in our presentation. We also did a lot more with our circuit schematics, kind of finalizing those and what it should look like when it's fully wired up, as well as our basics software flow chart for what the basics of what our code is basically going to be running. So for the microcontroller, we have it built and we were able to get it to run and accept code. As you can see here, we got the onboard LED to blink. The issue is when I was able to disconnect the Arduino and just put in the 9-volt battery to it, something was weird and it wasn't accepting the power, or it was overloading it where it wasn't working. But as long as the Arduino was still connected, it was able to run. So we are still troubleshooting that currently.
So for our ethical and professional responsibilities, we have 3 of them which we've worked on in the report. We have our global impacts, which we have interest in robots are increasing at a higher rate. With high schools now taking part in robotic competitions, and in fact, our competition, the hockey robot competition, is actually a high school competition that's happens. And then we have our economic impacts. So for this, parts are generally easily accessible for a lower cost. And our environmental impacts, robotics are taking larger roles in environmental cleanup and such.
So this is our circuit schematics for the ATmega 328 pinout. And this just makes it really easy for us to be able to use the ATmega as pretty much an Arduino for this project. And this will only be on the chassis of the robot vehicle itself. And here's the setup on how we're going to do that. So it has a voltage regulator to reduce the voltage and not burn the device. It has capacitors to give steady flow to the crystal oscillator, which is like the system clock for the ATmega. And also we added a normally closed button so that we can just reset the switch and make it easier for code usage. Okay, onto the controller. So we're gonna have a 9-volt battery source that connects to the raw input of the Arduino Pro Micro down there, as you can see. And when you plug that into the raw, it has a built-in voltage regulator, so it should be fine. The joysticks will connect to the VRX and VRY and to their digital outputs, or their ADC outputs, and as well as power on the ground. And we only need 1 joystick and something to activate the actuator and control the throttle. And the Arduino also connects to the NRF24L01 via a 3.3 voltage regulator, and just some capacitors overall to keep the voltage steady. And here's our overall circuit diagram for that. As you can see, we're utilizing the microcontroller with some resistors and some capacitors and some voltage regulators. We have the L298N motor driver for our 2 DC motors, the NRF for the antenna connection, and that'll be a 12-volt power supply with a programmer.
Here's our software flow chart. It's going to start with powering on, and then since this is all manual, it's a pretty simple program. It's going to await the user input from the controller. It's going to then take the value. For instance, the joystick has an X and Y value when the joystick's in the middle. So we're going to have 524. And then when it wants to go left and right, it's going to decrease and increase. So we'll take a ratio for the speed of the right wheel and left wheel to either go left, right, forward, backward. For the trigger, we are going to decide if we actually want to use that to regulate the speed or just have a kind of a default speed that we use. And then the other input will be, of course, our shooting mechanism. When we push that button, it's going to shoot our shooting mechanism and then it will reset. Then we'll have a delay there at the end of that loop and it'll reset back until we end up turning the robot off, which will then turn off the program. Some of the problems we ran through on these steps is we ordered the wrong micro Arduino. We actually ordered a 3.3 volts rather than a 5 volt, which isn't a huge issue, but we did order a 5 volt, and there was another remedy. If we want, we can convert the 3.3 to a 5 volt. It's just going to take a little bit more work, but if we do run into time constraints, we will do that, but we did order a 5 volt and that is on the way.